Hello everyone. My topic is towards automatically reverse engineering vehicle diagnostic protocols. This is my project title, and I had done research on this project. So starting with coming to introduction. So this project has mainly focused on producing an in-car protocols that are essential for coordinating the communication and management. So it has coordinated both of these of electronic control units that oversee various vehicle components. So now at present the current approaches are mostly concentrating on well-documented protocols such as CAN, and they are only able to comprehend and interpret the complexity of car diagnostic protocols. So this research, what is innovation has done in this research is it has designed to automate the process of these reverse engineering automotive diagnostic methods in order to close this gap. So they want to bridge a gap that is between the current approaches and for the future innovations. So this project has been focused and has used various robotics, sophisticated imaging, and professional diagnostic tools. Research framework aims to understand these protocols, revealing their forms, their implications, and their components. So then after this project has been done, they have successfully tested with 18 real cars that confirms the usefulness of this framework and represent a major step towards the knowledge and security of these vital vehicular systems. So this project has bridged a gap between the current approaches and the future work. So they has produced an in-car protocols that has used an electronic control units. So the more we are going to learn in the next slides. So now we are going to the importance of decoding vehicle diagnostic protocols. So, what are the importance and why are we doing this project? That comes here. The main important is one that it examines car diagnostic techniques which are essential to comprehend and protect contemporary vehicle systems. So, it examines and it also essential to protect the contemporary vehicle systems. And also, it offers crucial insights for improving security evaluations and mitigating possible risks. So it has taken several steps to improve the security, that is which most at most important, and also it has taken care to mitigate the possible risks. So one more important point is better defense against prospective cyber attacks is made possible by the research focus on reverse engineering these diagnostic signals, which closes a significant knowledge gap regarding proprietary formats. So it has also taken necessary steps to get prevention from the cyber attacks, which is most frequent in nowadays. And also, the researchers' effort greatly advances the creation of strong security protocols necessary to guarantee the integrity and safety of contemporary automotive systems. So this researchers' effort has in a greatest and advanced way for maintaining the security protocols. So these are the glimpse of importance of the decoding vehicle diagnostic protocols. And now we are getting to the threat model. That is one of the model that has been used in this project. And as we have learned in the introduction, this model has used electronic control units. So here we can see with the help of a diagram, there are many electronic control units that are connected to the other gateways over here. So the electronic control units of a contemporary car, here this is the contemporary car, are shown to be interconnected via bus systems, CAN frames for communication, and a central gateway. So this is the central gateway over here, And this is the domain gateway, and this is also a domain gateway. These are the two gateways, and these gateways are again interlinked with electronic control units. So in order to send and receive diagnostic signals for ECU interaction, the onboard diagnostics connection makes it easier to communicate with professional diagnostic equipment. So here it comes the OBD port. What is the OBD port? Onboard diagnostics. So this is interlinked with central gateway, and this central gateway is interlinked with domain gateway and with ECUs interlinked with. So the research has ramifications for attackers as well as from defenders. So as we mentioned, as we have learned earlier, it has maintained several security measures that it is well protected from the attackers and also from the defenders. And next, the project intends to improve knowledge of car diagnostic communication by reverse engineering protocols such as KWP 2000 and UDS in order to find crucial information that isn't stated openly in their specifications. So here what we have learned in this point is that it has extended his knowledge, and through the protocols such as it has used two protocols, namely KWP 2000 and UDS for the other information that is not stated over here. So we are going to learn that. Okay. And this is the system design, and it has implemented through this diagram. We can see how the system is designed in this project. At first, here this picture depicts that it has a robotic clicker and the two cameras are included at the sensor or actuator. And this is the actual layer. One takes screenshots to direct the clicker. So the camera A takes the screenshots, while the other records the user interface. So it records the user interface of the diagnostic tool for the purpose of reverse engineering. So for this purpose, it has included a robotic clicker and also two cameras. The control scripts are sent to the actuator via USB connections. So here from the actuator, it has sent me through the USB connections, and screenshots from camera A are transferred to a laptop as part of the communication layer. So the whatever screenshots the camera A takes, it has transferred to a laptop as a part of a communication. These screenshots are analyzed by laptop's application layer, which then creates control scripts for the clicker. So the screenshots that has been taken by the laptops, it has sent to the application layer, and from then it creates a control scripts for the clicker, as we can see from the above image. Okay, and in parallel, the system listens for and records CN frames that are sent back and forth between the car and the diagnostic instruments. So here we can see, so this camera has sent to the UI analyzer and planner and script organizer, and again the scripts are sent to the script executor and logger, and again this one has sent to the application layer, and these are interlinked. That is, in parallel system design is sent back and forth between the cars. So these scripts are sent back. It is a cyclic process for the reverse engineering method. So this is the system that has been designed for, and now we have come to the investigation, like what the researchers has done to analyze the information. So they have used these 5 steps. They have used the data collection, diagnostic frames analysis, screenshot analysis, request message analysis, response message analysis. These are the step-by-step process that the investigators has used in this project. So we will learn step by step in the next slides. So firstly, we have come over here with the data collection. So the DP reverser system automatically captures UI films and CAN messages using a robotic clicker. So as we have seen in the previous slide, so the robotic clicker has automatically screenshots using a robotic clicker. It takes the screenshots, and the robotic clicker is directed to engage with certain regions of the diagnostic tool by a UI analyzer. So here is a UI analyzer, and it will send the pictures to the UI analyzer, and the target ECUs are sent to the planner. See, wait durations are collected throughout script execution, and timestamps are used to guarantee appropriate tool replies for data segmentation. So in order to divide the data according to the organize the data, so we have used the timestamps and script execution for the data segmentation. So as we can see here, the target ECUs are sent to the planner and order of clicking. So on the first come first serve basis, the order of clicking of the ECUs is sent to the script generator, and then the scripts are finally sent into the script executor and logger. And again, this script executor and logger will send again to the application layer of the laptop. See, CAN frames captures made during tool vehicle communication and user interface test records linked to certain timestamps for reverse engineering. So these frame captures are also interlinked with the user interface for the certain timestamps for this process. So this is overall the data collection method, the first method that is used by the investigators. And next, coming to diagnostic frames analysis, these here in this analysis, we have used different frames for analyzing the data. So in the first frame, we screen incoming frames, removing non-payload frames and keeping pertinent frames such as single, first, and continuous frames. As we can see here, these are divided into 3 frames. So here we'll be removing the non-paired frames, and we will segregate the frames into these 3, that is single frame, first frame, and the continuous frame, depending upon the data payload. Okay. Second, we handle changes in transmission protocols, including the unique storing of ECU IDs in some cars by reconstructing fragmented diagnostic message payloads scattered over many frames into whole messages. So here we will do this so that the sender and the receiver, here we will scatter the frames into the messages. Okay. Thirdly, we ensure dissection accuracy by carefully extracting important components from built payloads such as local IDs, data IDs, electronic system values, and control records. So by using all these components, we ensure the accuracy by extracting information from these components. So here we can see flow control frame. So here we will do all the accuracy of the information from these components that has been mentioned now. This altogether we call it as diagnostic frames analysis. And now when coming to screenshot analysis, in this analysis, we make use of OCR technology, namely Tesseract, to extract semantic information from user interface video test. It also allows us to capture important elements such as the semantics of requested message and computed electronic system values that are obtained using formulae. It also includes a post-processing phase to guarantee data extraction accuracy by using amplifier to convert the video stream into pictures in order to do tesseract processing. So, to further improve the derived ESV values, this method includes a 2-stage filtration process. So, the next step is request message analysis. The UI display tests are a means of recovering the functionality of standardized values for fields in request messages that lack semantic meanings. So, here the request message contains device IDs or local identifiers customized by manufacturers when reading electronic system values using UDS or KWP 2000. So here in this figure we can see it has request and positive responses. of the read data by local identifier service of KWP 2000 that we have learned now. And this is one that is uses UDS. Okay. In order to interpret the meaning of these IDs in request messages, we either extract the ESV kinds that are visible in the user interface or determine the kind of controlled component. So here we have used KW to be 2000 and here we have used UDS for request message analysis. Okay. And this is response message analysis. And this is the last step in the data collection, that is the system design. So in this analysis, the diagnostic tool compares the ESV in UDS and KWP 2000 answer messages. So it is here we can see that it has compared ESV in response messages, ESV replayed in UI. So it compares between these two components, and generic programming can handle both arithmetic operators and non-linear functions by employing timestamps to create a relationship between the ESV of the diagnostic message and the ESV displayed on the user interface. The procedure leverages genetic programming to explore mathematical expression spaces in order to derive formulae. So here are the mathematical expression phases. So here we are derived the formula using all this. So we have compared these two: pre-processing of the data set and the post-processing of the variables contained in the formulas inferred by GP. So here is a comparison between the pre-process and the post-process. To get the best accuracy, pre-process the data set and post-process the algorithms. The most accurate results are obtained by aiming for an absolute UI-ESV range of 1 to 10. So we have obtained the range from 1 to 10. Okay. And now when compared to all the analysis, what are the results we obtained is, with regard to UDS and KWP 2000 frames, DP reverser outperformed other algorithms exhibiting notable accuracy. Additionally, it emphasized the ways in which telematic applications and specialized instruments for diagnosis differ from one another. So, the expert instruments had more aptitude for recognizing ECUs and deciphering environmental sensing values, in contrast to their application equivalents. So, this work greatly expands on our knowledge of how well DP reverser extracts textual information using different diagnostic devices and procedures. So, it also highlights how well it can get formulae from particular diagnostic frames and how different diagnostic tools and applications can decode ECU data and read values related to a given protocol. So here are the key results that we had done, that we have obtained from using this analysis and project. And here we can, when we come to the mathematical values, so here is the analysis of all those we have done. The precision of the USR engine reaches 97.6% for RTL 919 and 85% for launch H431. The CAN frames of reading 7 times of ESVs with OBD2 protocol, the precision of reverse engineering is 100%. The frames of reading 290 types of ESVs with UDS or KWP 2000, the precision of reverse engineering is 98.3%. 32% CAN frames for UDS and 75.2% CAN frames for KWP 2000 must be processed by payload recovering. Otherwise, the fields in them cannot be extracted. Moreover, when inferring formulas, the linear regression algorithm only achieves 43.8% precision and the polynomial curve fitting only achieves 32.1 precision. The precision is much lower than that of DP reverser. For the 124 ECRs of 10 vehicles, we correctly extracted all ECRs. We also find that 3 messages are required to control each vehicle component by using the input-output control service. These are the key points of our analysis that we have done in our project. So this is the related work. So different techniques have been developed to reverse engineering message formats from systems such as CAN communications and SCADA messages. The read algorithm in recognizing message fields and ECU signal values, but it encountered various difficulties. So while trying to extract diagnostic absent messages, CAN enter and other tools lacked a thorough study of the diagnostic methodology. So in order to recover message formats, dynamic tools such as Polyglot, Dispatcher, and Auto Format use techniques include taint analysis, backward analysis, and execution context grouping. So this is the related work we have done. And coming to the limitations, there are three limitations that we have faced in this project. Restrictions on the need for particular tools, software, or hardware applications which may not be available everywhere or may demand a higher level of access. So we have a limitation on the particular tools and software or hardware applications, and also various messages, field lengths, nonlinear interactions between fields and signals, and constant value identification. And the other limitation is accurate field extraction is further impacted by challenges in interpreting lengthy messages sent over network or transport layers. These are the limitations that we have in this project. And the future work corresponds to, in order to enable DP reverser to tackle increasingly challenging reverse engineering issues, we are first preparing to handle complicated, non-trivial formulae found in diverse diagnostic methods. We are also working to strengthen the functionality of the OCR engines that are included into the tool. In order to enable DP reverser to complex systems seen in automobile technology, we are also enhancing the tool's capacity to examine advanced telematics applications. These are the future work that the researchers mentioned in this project. And the last coming to the conclusion, DP Reservoir presents an innovative automated framework that has been created especially for deriving car diagnostic protocols from professional diagnostic equipment and reverse engineering them. DP Reverser is skilled at extracting the proprietary formulae that are used to analyze the answer messages. By means of its deployment and comprehensive testing on 18 distinct automobiles, DP Reverser demonstrates an extraordinary ability to precisely and efficiently reverse engineering complex data included in the request and answer messages of expert diagnostic instruments. So these are the acknowledgement. Thanks to Professor Van Thorn Pam, Hong Kong ITF project, Hong Kong RGC project, and also the fundamental research funds for the central universities and the National Science Foundation that has helped in building the information for this project. And at last, thank you. Thank you everyone for your support. And yeah, thank you.